Hi everyone, and welcome back to another AP Calculus video. Today we're going to continue our conversation about infinite series and how we can take an infinite series and represent it as a function. Now, up to this point, we've only talked about geometric series. So let's kind of review what's happening here. If we have a function like this and we want to identify, find a series that represents this function, we would remember that in a geometric series, we have this formula, s equals a, the first term, and then 1 minus r. So kind of drawing parallels between these two things, what I would do is I'd say, well, here's r, and this must be a. So as long as I can get it to resemble this formula, I can pluck out the a and the r. And if this is a geometric sequence, or sorry, a geometric series, remember the only difference really is that in a series we're taking those terms and adding them together. If r is x squared and a is x, then our general geometric series, or our sequence anyway, the general rule for that, remember it's a1 times r to the n minus 1. So here we would write down an equals a1, which is x, and then we'd have x squared to the n minus 1. Now, as we're considering this, because we want to find a series that represents this function, we're then going to take and put it into series notation. So we're going to draw our little sigma, and we're just going to plop our rule right in there. And we're going to go from infinity, or to infinity. Now, where we go from really kind of depends on what we're doing here and what we're looking at. Now, if I try to create a series, I have to be careful at what I start n at. Whatever I start n at, I want to basically take this term here and make it equal to 1 so that x is my first term. So the way that I do that is I need n minus 1 to equal 0, so I have to start n at 1. Now, that's all well and good, except that most of our series, when we're dealing with these geometric series, most of the time they start at n equals 0. So all that means is now I'm going to take and adjust. So remember, when we have a series, if I just change the exponent a little bit, I'm going to make it n, and then I can start my series at 0. So whether you start at 1 or 0 really doesn't matter, and there's no real good nailed down, this is how you should do it every time. Most of the time we start at n equals 0, sometimes we don't, and it all has to do with what the first term is. So really where you're starting your series at is n equals 0, n equals 1, really depends on your exponent and how that gets you to having your first term. So generally we like these series to start at n equals 0. Now check this out. If I'm going to rewrite this series, I can rewrite it in a few different ways. So I'm going to go ahead and continue with this series, and I'm going to write it like this, x times x to the 2n. Now, I'm also going to notice that I have x times x to the 2n, and the exponent for just plain x is a 1. So another way that I could write this series is like this, from n equals 0, and then I would have x to the 2n plus 1. Now this would produce a series that looks like this. When I plug in 0, I'd start with x, there's my first term, and that holds true with what I said would happen in the beginning. And I'm going to add to it, and it ends up being all of the odd powers. So when I plug in 0, I get x to the 1. When I plug in 1, I get x to the 3, plus x to the 5th, plus x to the 7th, plus dot, 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 dot. And when we represent this function, which let's zoom out and remember, this is x over 1 minus x squared. When I represent this function, the whole point is this x should be my first term, and then every time I go to the next term, I'm simply multiplying by x squared. And it all kind of goes full circle, and we see it all play out in this way. Now, if I'm going to write a series out, an infinite series, I want to make sure that I also I include the rule, the general rule is what we call it. So the general rule here is that x to the 2n minus 1. Now, I'm going to go plus dot, dot, dot. When I take my AP exam and I try to represent a series, or represent a function with a series, I always want to make sure that I include two things. I want to make sure that I include the first few terms. Oftentimes it'll tell me first 3, first 4. And then I always need the general rule. On the AP exam, in general, you get a point for the first couple of terms. They'll specify how many they want. And then you'll get a point for the general term. This is what this is called. So here we have this geometric series represented in in sigma notation, but also represented in written out series notation. And you'll know which notation to use because in the exam it'll say write the first 4 terms and the general term. And this is the format that you'll want to write it in. Sigma notation is fine otherwise. These produce the same thing. So as we are representing functions with a series, what I want you to pay attention to is that for this function, we will line right up. This polynomial that goes on to infinity will match the graph of the function that we started with, but only on that interval of convergence. So let's talk about what the interval of convergence is. Now remember, this will converge, this series will converge for any value of x or any value of r, provided that it's between 1 and -1. So let's recall we have this rule. The absolute value of r has to be less than 1, meaning r has to be between positive and -1. So what I do is I say, well, x squared is my r, and I'm going to plug that in. Now, x squared can't be negative, so I'm just going to kind of ignore this for the moment. And I'm going to deal with this. X squared has to be less than 1, because here's what's going to happen. When I square root x squared, I get the absolute value of x. Oh, which anytime I have the absolute value of x, I'm just going to rewrite it like this, -1 to +1. So here's my interval of convergence. Anywhere between 1 and -1, this polynomial that I just wrote will line right up with that function. And if you were to go to Desmos and graph the two, you would see that they would line right up, just kind of like what we did in our previous video. Now, this method works wonderfully when we are dealing with geometric series. When you deal with a geometric series, when you're going from a function to a series, this is what you want to do. You want to identify r, you want to identify a, and try to write that general rule and generate the series. Now, you can also generate it by saying, hey, my first term is x, and I'm multiplying by x squared. You can see that that's one great way to do that. But then you're going to have to figure out what that general term is so you can get full credit. But then the question arises, what happens when we have a series that doesn't follow a geometric pattern and it follows some other kind of rule? Well, this has been discussed. When we have a non-geometric function, is it possible to construct a series that would converge to something like e to the x or sine of x? Now, this is the question that Brooke Taylor and Colin McLaurin are credited with kind of dealing with and answering. So these are the mathematicians. Now, Brooke, one too many O's in there. Brooke Taylor, I should spell the guy's name right? Brooke Taylor was a English mathematician, a British guy, and then Colin McLaurin was Scottish. And these guys both studied looking at functions and saying, well, can I model the function with a polynomial? And what they came up with was they said, well, if I have a polynomial and I construct a polynomial around some information that I know. So for example, let's say that I know the behavior at a single point. So for example, e to the x. I know that at 0, e to the x would be 1. So I know what the y value is. I also know the behavior of the derivatives because I can evaluate the derivative of e to the x. And they said, well, if I know all the derivatives and I know how a polynomial works, as I take the first derivative, I should get this result. As I take the second derivative, I should get this result. And if they know all of the derivatives up through a certain point, they can construct a polynomial that will have the same derivatives, which is what we're about to do right now. So let's take a look. Suppose we have this polynomial, and we're only going to go to x to the 4th power, and it has this behavior here. We want to make it so that the first derivative, or so that the y value at x equals 0 is 1. We want the first derivative at 0 to be 2. We want the second derivative to be 3, and so on and so forth. So let's think about this. What I need to do is I need to say, well, as I do the polynomial, I know that a0, when I plug in 0, every single one of these x's is going to go away. They're going to go to 0. So by knowing this, I know that a0, the very first term, is going to equal 1. That's easy enough to see. But now let's talk about the second derivative. The second derivative, when I go and I try to take the derivative of this polynomial and plug 0 into it, keep in mind that the squared term, the cubic term, the quartic term, all of these terms will still hang out. And when I do the derivative, there we go, when I do this derivative, this constant term is going to go away, and I'm just going to be left with p prime is going to be a1 plus 2a2 plus 3a3 plus, squared, plus 4a4 to the third power. And when I plug 0 in, all of these terms are going to go away, and I'm going to be left with a1. And so that tells me that when I plug 0 in, I want to get 2 as my answer. This is saying that a1 must be 2. Now, if we continue on with our logic and we find that second derivative, a1 will go away, and I'm going to be left with 2a2 plus 6a3 plus 12a4 squared. Now, x, forgot my x's. Those are important because when I go to plug in 0, all the terms with x's will go away. And what I want to have left is 3. So I know that 3 has to be equal to 2a2. Well, guess what? That means that 3/2 is my a2. Let's continue the pattern out. I'm going to take the third and the fourth derivatives here, and we're going to see what happens. So here we are with the third derivative and the fourth derivative. And notice once we get past about the third derivative, we start using that little notation with the 4 in the parentheses. It just gets a little crazy with all those little comma or apostrophes up there. Now, you'll see that as we did each derivative, that constant in front of the a3 or the a4 was being multiplied by the exponent each time. So you couldn't just jump in and say, oh, the coefficients are 1, 2, 3, 4, 5. No, the coefficients are involved with the answer here. Whoops, and I rewrote that wrong. 5/24. But you'll notice 1, 2, 3, and 4 do show up there, but we're always dividing by that constant. And think about where that constant came from. As we multiplied and took each successive derivative, we kept multiplying by the exponent. So we'd multiply by a 3, and then a 2, and then a 1. That x to the fourth we multiplied by a 4, and then a 3, and then a 2, and then a 1. And you might be thinking to yourself, gee, when I go and I write this polynomial, which is going to look a little bit like this, so now p of x is equal to, remember we want a0 is 1, plus 2x, plus 3/2 x squared, plus 4/6 x cubed, plus 5/24 x to the fourth. You might be noticing some things, and one thing I want to remind you of is as I look at these denominators, remember they came from saying 2, 3, or 3 times 2 times 1, and 4 times 3 times 2 times 1. And you'll notice that this 24, as I did each derivative, came from 4 times 3 times 2 times 1. This 6 came from 3 times 2 times 1. This 2 technically came from 2 times 1. And you'll notice that there's this little pattern here. And when you multiply an integer all the way down to 1, we call it a factorial. So another way to express this is using this exclamation point. When you see this exclamation point for like n factorial, or like let's say we had a number 5 factorial, what that means is I'm going to take this number and I'm going to multiply it by every value less than it by 1. Okay, so n factorial would be n times n minus 1, so 1 less than n, and then 2 less than n, and so on and so forth. That's what n factorial kind of really means for us. Now, looking back at what we have this little pattern where if I rewrite this using that factorial, I have 1 plus 2x plus 3x squared over 2 factorial plus 4x cubed over 3 factorial plus 5x to the 4th over 4 factorial. Let's identify a few key features here, and we're going to show a little bit what's going on. What we've just discovered is that there's this pattern happening where if I know what the derivatives are, keep in mind my derivatives were 1, 2, 3, 4, and 5. And each of these powers squared showed up in the denominator as a factorial. Well, Brooke Taylor and Colin McLaurin both identified this pattern, and they said, this way, if we know what the derivatives are, the first handful of derivatives, we can write a polynomial that represents my function, whatever that function is. And so notice we've got f of 0, f prime, f double prime, and then this notation f to the n, or that means the nth derivative. So we can take whatever derivative we're going up to. And then the factorials show up like this. We've got x and x. We've got x squared over 2 factorial, and then x to the n over n factorial. And the key is that pattern continues on. And the more terms we add, the more accurate we get. But it also means the more information we need to know about our function. But essentially what this means is if I have any function, I can write a polynomial that will represent this function and line up with it, for a while along its interval of convergence. Now that interval of convergence is something we're going to talk about later on. For now, what I want you to know is how to construct this polynomial. And we can often refer to this as a Taylor polynomial. And this particular polynomial is centered at 0 because that's the point where we know all the information. We knew the derivatives at x equals 0. We knew the value of y at x equals 0. We also are going to talk a little bit about what happens if we want to center it at a value other than 0. That's going to be a little bit later on. But this is called an nth degree Taylor polynomial. Now Taylor kind of gets the glory here. But Maclaurin actually did a lot of work with this, and a Maclaurin polynomial or a Maclaurin series is an infinitely long polynomial. We also can refer to that as a Taylor series, but a series just means it's infinitely long. The moment we call it a Taylor polynomial, it just means we're going to stop. We have a set point where we're going to stop, x to the 4th power, that's it. We can't go on forever. So a polynomial stops, a series goes on forever. Now, we'll talk about some of the differences, but just know that Taylor and Maclaurin essentially mean the same thing. But let's see if we can practice. We want to construct a 4th degree polynomial, Taylor polynomial, for the function f of x equals natural log of 1 plus x. Now, in order to do this, we need to know some derivatives. So we're going to be centered at x equals 0. And all that means is we need to know the behavior at x equals 0, wherever our center is. So let's get started. We need to know f of 0. So I'm going to call this n equals 0. It's my 0th term. And all that means is we haven't done any derivatives yet. I need to know my first derivative. We're going to call this n equals 1. So this is f prime of 0. And then I need to know all the way up through 4th degree. 4th degree means you're going to go up through n equals 4. That means it's the highest power in your polynomial. So let's just kind of do a couple easy things. F of 0 is the natural log of 1 plus 0. That's the natural log of 1. That's 0. That's easy. F of 0 is 0. Now let's find our first derivative. So in order to find f prime of 0, we first need to find f prime of x. Well, doing my derivative, it should just be 1 over 1 plus x. So that means f prime of 0 is 1 over 1 plus 0, or 1. So that's easy. That's going to be, that's going to be kind of this value right here. Okay, so we have 0 That's going to go in here. We're going to kind of color code. Now let's keep on going. N equals 2. That means I need to know the second derivative of x. That means I have to take the derivative of 1 over 1 plus x. Okay, I happen to know that it's negative 1 over 1 plus x squared. Because remember, this is 1 plus x to the negative 1. So when I do that derivative, I'm going to use the power rule. And that's going to be kind of what I do each time. So now f double prime of 0 is negative 1 over 1. That's negative 1. So this is going to go right there. Okay. Now if I keep on going, let's go ahead. N equals 3. That's going to be f triple prime. And finding that derivative, I'm going to get 2 over 1 plus x cubed. So f triple prime of 0 is just 2 over 1, which is 2. So that is going to go, well, somewhere. That'll be the next term. It's not listed in there. But then lastly, n equals 4. So this means it's a 4th degree polynomial. That means the highest power I'm going to have in C is a 4. So f, the 4th derivative of x, turns into negative 6 over 1 plus x to the 4th power. And when I plug in 0, I get negative 6 over 1, which is just negative 6. So now we're ready to construct our polynomial. And following the convention here, remember, when I have the powers, so like squared, it's going to be a 2 factorial underneath. So whatever the power is, it's going to be that number factorial. So let's write it out. So here we go. My 4th degree polynomial, sometimes we put the little 4 down there just to say, hey, it's a 4th degree, whatever. It's going to be f sub 0, or f of 0, which we said was 0. F prime is 1. And then f double prime. So n is 2. So whatever derivative is, the second derivative means it's going to be the second power and a 2 on the bottom. So I'm going to have negative 1 x squared 2 factorial underneath plus. Then I'm going to do the third derivative. So this is term where n is 3. So I'm going to have 2, that was my third derivative that we found, x cubed over 3 factorial. Lastly, I'm going to do my fourth term. I'm going to have negative 6 x to the 4th and then a 4 factorial. So what I've just done is I've constructed these terms for the 4th degree polynomial, and that just means that the highest exponent is a 4. We just go up to where n is 4. We're always kind of starting where n is 0. That means it's f of 0. We haven't done any derivatives yet. Now if I wanted to simplify this, I could. I'm not gonna. I'm gonna leave those factorials. As long as you know how to multiply them out, you can leave it. You don't have to write the 0, so you're just gonna go x minus x squared over 2 factorial plus 2x cubed over 3 factorial plus negative 6x to the 4th over 4 factorial. Now suppose we did want to write this and kind of turn it into a Taylor series. Here's kind of how I would deal with that. Let's get ourselves a little more room. If I wanted to write the series, what I might consider doing is saying, well, I'm going to take this polynomial and I'm going to write out the factorials. I'm going to have x squared over 2. And then because I know that this number here is going to be 6, 3 factorial is 3 times 2 times 1, that's 6. Well, 2 over 6 reduces down to x cubed over 3. And I also know that this is 24. So negative 6 over 24 means I'm going to have minus x to the 4th over 4. And you notice there's this pattern happening where it's this alternating series. Now, if I wanted to write the Taylor series, I would have to come up with, the nth term, the general rule. And so I notice here, if this is n equals 1, because we kind of cut out n equals 0, this is n equals 2, n equals 3, n equals 4. Notice the exponent and the denominator are the same. So what I'm going to do is I'm going to say, well, it's just x to the n over n. But then because the sign is alternating, I'm going to throw a little alternator in there, negative 1. Now, here's where it gets tricky. I have to decide, is it to the n or is it to the n plus 1? Now, if I do to the n, back here on that first term when n was 1, I would have a negative sign in the front. Because I don't have a negative sign in the front, the negative is the second term where n is 2. I'm going to take and I'm just going to go plus 1. That shifts that negative to the next term. I always have to look and see, do I have the negative right? And then plus dot dot dot. This is the Taylor series. All a series means is it has that general term, it goes on forever. The polynomial goes on until, fourth degree when it tells us to stop. So let's see another example. Let's see what's, involved in writing some more polynomials here. So we are going to construct now a 7th degree polynomial for sine of x, and we're going to center it at x equals 0. Then we're going to show the Taylor series. So like I said, we need to know a couple of things. If we're centered at x equals 0, we need to know f of 0, f prime of 0, f double prime of 0, and we're going to the 7th degree. So the 3rd derivative at 0, the 4th derivative at 0. Wow, look at all these derivatives. The 6th and the 7th. All right, well, let's go ahead and write a couple of things down. Now, if we're doing sine of x, I know that this is going to be sine of x when x equals 0. But then I'm going to go ahead and I'm going to remember my wheel of signs. This will make it nice and easy. So I started at sine. The next one's going to be cosine. The next one's going to be negative sine. Negative cosine, sine, cosine, negative sine, negative cosine. So let's go clean it up. So I'm making sure to use proper notation here. All right, so let's evaluate. So the sine of 0, okay, sine of 0 is 0. Cosine of 0 is 1. Negative sine of 0 is 0. Negative cosine of 0 is negative 1. Ooh, I see a pattern emerging. Okay, there's my pattern. So now let's write our polynomial. So P7 of x, all right, remember it's f of 0, which is 0, plus f prime times x, x to the 1 over 1 factorial, plus the second derivative, 0x squared over 2 factorial, plus negative 1x cubed over 3 factorial, plus, now the fourth, 0x to the 4th over 4 factorial, x to the 5th over 5 factorial, 0x to the 6th over 6 factorial, plus negative 1x to the 7th over 7 factorial. Now notice what's happening here. You've got some of these terms canceling out, and it happens to be all of your even terms that are going to just go away. So when I rewrite this, here's what happens. I have found that the Taylor polynomial is this. The 7th degree polynomial is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. There's my 7th degree polynomial. Now if I want to write the series, here's what I have to do. I have to come up with that nth term. So let's see if we can generalize. And instead of saying p of x, really what I should say is that sine of x is equal to, I'm going to write out these first couple of terms, just going to rewrite them, 3 factorial plus dot 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 plus. I'm going to put that in there to say, hey, there's a bunch of stuff in here. And then my nth term, let's think about this. It's odd numbers, so it's going to be x to the 2n plus 1 over 2n plus 1 factorial Now notice it alternates. So I'm going to throw an alternator in there, and then I'm going to go here and I'm going to look. Now remember, this is when n equals 1. Okay. Now what we've just done is we have shifted our series so that instead of having to deal with n equals 1, n equals 3, we're still calling this, we're renumbering our series. So n equals 1, n equals 2, n equals 3, well, which means this needs to be 2n minus 1. There we go. So 2n minus 1. That allows me to plug 1 in for n and get the right answer. 2n minus 1, that's going to give me 1 factorial. I'm good to go. Now the first term is positive, but the second term is negative. So when I put this in, I need to make sure that I go n plus 1. It's as easy as that. What that does is it says, hey, when n is odd, I need to be positive, so I need to make it an even power. So how do I make it even? I go plus 1. So it just shifts that negative sign to be with the x cubed. And this is the general term for sine of x. And this is a Taylor series. Now, if I wanted to write this in sigma notation, here's kind of what it would look like. I would take that general term, and I would say, you know, sine of x is equal to, and all this does is it condenses it down, n equals 1, and I could go negative 1 to the n plus 1, x to the 2n minus 1 over 2n minus 1 factorial. Now, in keeping with our conversation about how these series are and how you can rewrite them, oftentimes instead of saying 2n minus 1, sometimes we'll start that series at n equals 0. So if we start at n equals 0, let's go ahead and just rewrite it real quick. If we start at n equals 0, then my nth term looks just ever so slightly different. I'm still going to have negative 1 there to some power of n, but this time it's just going to be to the nth power, because when you do negative 1 to the 0 power, it makes it positive, so I don't need to worry about doing the plus 1 if I start at 0. You have to back it up or move it. You have to shift it 1 some way, shape, or form. So if you're starting at 1, you can shift your exponent. You can also shift your n to start at 0. And if we do that, here's what it ends up looking like: 2n plus 1, and then 2n plus 1 factorial. And what this does is it says, okay, n equals 0, n equals 1. Well, 2n plus 1 gets me to the 3. 2n plus 1 gets me to 5. 2n plus 1 gets me to 7. So by starting at 0, we just adjust our exponents. Now, is there necessarily a right or a wrong way to do this? Nope. Unfortunately, it's just kind of like make sure that it works. And if it works, you're going to get credit for it. But in general, you'll see that Taylor and Maclaurin both started their series when they talked about sine of x and also cosine of x. They started their series with n equals 0. And generally, that's where we start most of our series. So it's always a good place to start. So to kind of recap what this video has kind of discussed and been about is this concept that if we know the behavior at a single point of a function, so for example, all the ones we saw today, we knew what the behavior at 0 is. If we know the behavior, we can construct a polynomial that will have the same behavior. In other words, it'll have the same first derivative, same second derivative, same third derivative at 0. And we're going to start seeing as we move forward and explore more of these, that these polynomials will match the graph. So the polynomial we constructed for the sine will match the graph of sine. And the more terms we add to it, the more it will line up, the closer it will be within whatever the interval of convergence is for that particular problem. So this is a simple process, nothing crazy just yet. Make sure that you guys are continuing to watch the videos. In the next video, we're going to talk a little bit more about this concept, and we're going to see what does it look like instead of focusing on centering at 0. What happens if we want to center it somewhere else? And what is that going to look like? We're also going to be taking a look at some graphs and diving a little deeper into this concept. But for now, my encouragement is to practice and to get this process down. And the more you practice it, the more it'll be in your memory and the better you will get. You can do this. Keep going. You've got this.